In this video, we'll discuss the linear dependence between three vectors a1, a2, and a3 that I've given here. And notice that the third vector depends on some parameter h which hasn't been specified. And the first question I want to ask is, for what values of h is this set of three vectors linear dependent? In order to answer that question, I'm going to let A be the matrix whose columns are the three vectors, and we want to know, are there linear combinations of those that give me zero, non-trivial linear combinations of those that give me zero vector. So in terms of a matrix equation, does the equation AX equal to 0 have a non-trivial solution? If the answer is yes, there are non-trivial solutions, then they're dependent. If there's only the trivial solution, then they're independent. So we should look at the augmented matrix that goes with the system. I put the three vectors down the column, and we want it to come out to 0, so I put 0 in the final column. You do your row reduction, which I'm going to skip in the video, and when you're done, you get something at some point that looks like this. You'll have h plus 10 in the third row here. And maybe we should think about whether or not h plus 10 is 0 or not, and that would decide how we should proceed. If it's equal to 0, then I'm just going to replace it with 0 there, and we're row equivalent to this matrix. You can see that it's consistent. We know it's consistent at the beginning because at the very least there's the trivial solution to this equation, so it had to be consistent anyway. And there are two pivots, not three, and so unfortunately, or depending on your view, there must be a free variable. That means we have non-trivial solutions, infinitely many non-trivial solutions, and therefore the vectors are dependent. The other case is when h plus 10 is not 0, in which case I can take h plus 10 and divide by it. I'll get a 1 there, and I'm closer to my reduced echelon form. But notice that nothing's really changed substantially here. I still have two pivots, and there's still a free variable. So it's non-trivial solutions to the system, and it must be dependent. So it didn't matter what the value of h was. The conclusion was that this set of vectors is dependent for all values of h. It wasn't hard to see this in this particular example only. It wasn't hard to see this just by inspection. That second vector is in fact 3 times the first vector. And there is a linear dependence between two of the vectors in this set, and that's enough to conclude that the set itself is dependent. Let's look at a related question, but different question. Here are the three vectors again, and I want to ask now, for what values of h is the third vector in the span of the first two? So can I force the third vector, by choosing h carefully, to be a linear combination of the first two? To answer that question, I'm going to let A be the matrix whose columns are only the first two, because I'm interested in their span, in other words, their linear combinations. And the question is now, does the equation AX equal to A3, I want it to come out to be A3, does it have a solution? Is it in fact consistent? This is different than before. We looked at the homogeneous equation, and we asked whether it had non-trivial solutions. Now I'm just looking at the non-homogeneous equation, and I'm asking whether or not it's even consistent. So you look at the augmented matrix. In fact, this is the exact same matrix as the previous question. We just had an extra column of zeros that ultimately added nothing to the calculation. So the row reduction can be gleaned from the previous slide. And notice that although I have one pivot here, I'm missing a pivot in the second column. Notice that the big problem, regardless of what h is this second row. It says 0 times x2 is equal to 1. That can never happen. That's a contradiction, and therefore it can never be consistent. It had nothing to do with what happened in the third row, and we can come to the conclusion that A3 is never in the span of A1 and A2. You can never choose h to make that happen.